Hey, Dr. B here, and this is an introduction to buffers. These are systems that contain both acid and base, and specifically, they are those systems that resist a change in pH. That's a pretty specific thing. I mean, after all, just a garden variety acid like, say, vinegar, which is acetic acid in water, if there's H plus in there, and there is, there also must be OH minus, less, since the H plus times the OH minus concentration multiplies through to 10 to the minus 14th. But that will not resist a change in pH. There is a specific system which tends to do that. It's a weak acid or a weak base. That means acids or bases that don't dissociate much. For example, there's a weak acid, acetic acid. But present also is you must have significant amount of its conjugate. For a conjugate base, that would be what forms after acetic acid loses its H+, and that's acetate, C2H3O2 minus. For a weak base, that would be its conjugate acid, what happens after it gains H+. And that would be a different case, which we'll show you an example of. Ammonium chloride, for example. Why does it work? Well, both the acid and the base stay present in the solution and they resist that change. Let's look at the two scenarios. So we're adding H plus to our buffer system. What will happen? Well, it will react with that conjugate. So it will react with sodium acetate to form acetic acid, right? So it will form that in the form of acetic acid, but being a weak acid, it doesn't dissociate much. So it'll dissociate a little bit, making it a little bit more acidic, but on the other hand, you're decreasing the concentration of that conjugate base, so they offset each other. There's not much change in pH. Suppose you add some base. Well, that will react with the acid, which would be the acetic acid, for example. I get that. It'll make acetate, right? But acetate in itself is a base, so that increases. Once again, we have a offsetting situation. This goes down a little, this goes up a little. That brings the pH down a little, that would bring the pH up a little. Changes not much. So these are buffer systems. All right, here's some combos. Tell me if they are buffer systems. Phosphoric acid, to which people have added potassium dihydrogen phosphate. Well, that is a weak acid. It's not on our big six list. That is its conjugate base. I like it. Sodium perchlorate and perchloric acid. Well, sodium perchlorate is the conjugate base of perchloric acid. That's what would happen after you add, say, sodium hydroxide to it. You will get sodium perchlorate and water. So, yeah, it's looking good. Hold on. Perchloric acid is a strong acid. So if any of it formed, it would dissociate 100%. So that does not belong. So no. And here is, what is that? Looks like it could be triethylamine, I believe. And this is triethylammonium chloride. There's probably other isomers possible too, but these organic amines are weak bases, and this is the conjugate acid, so I like it. Hydrochloric acid, to which somebody added potassium chloride. Well, once again, potassium chloride is the conjugate base of HCl. After all, it lost its H+, but no, because HCl is a strong acid. However, if we have HCl and we add sodium acetate, this is the tricky example that you have to think about, for example. Clearly, sodium acetate is not the conjugate base of HCl. However, if you throw those two things in solution, the sodium acetate will react with the HCl, pick up the H+, and you'll have some sodium. If you have excess sodium acetate, well then, yeah, you would have acetic acid and sodium acetate. So it made a buffer system. And it's only true if you got excess acetate, because if you don't, then you'll still have some strong acid in the solution, which would just dominate everything. So that's the tricky one. Yes, if you use excess acetate, and that's the important chemical reaction there. It consumed all the HCl, and you now have acetic acid and sodium acetate. That's a buffer solution. Okay, that's an introduction to buffers.